Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be going over how to determine the partial pressures of products after a reaction has occurred in a vessel in which you have a valve that you can open to get the reaction to go. So let's get into this. So here we have a nitric acid, or I'm sorry, nitric oxide, NO, reacts with molecular oxygen as follows. So we have 2NO gas reacts with O2 gas to give us 2NO2 gas. So initially the NO and the O2 are separated as below. So here we have NO gas on this side of our vessel, and it has 4 liters, and it's at a partial pressure of 0.500 atmospheres. And then on this side we have O2, and that's at 2 liter volume here on this side. This has 2 liters, and it's at 1.00 atmospheres. And so this is closed right now, and so these are separated. So this is a 4 volume part, and this is a 2 volume part with the partial pressures right now. And then it says, initially they're separated as shown below. When the valve is opened, this valve here, when that is opened, the reaction quickly goes to completion. Determine what gases remain at the end of the reaction and calculate their partial pressures. And we're to assume that temperature is constant. And so temperature is constant here. And so what we're going to do is we have to start by labeling everything, pulling everything out of the problem. So here, pretty much everything's here. So before the reaction goes, we have the pressure of NO, and we have the volume. And here we have the pressure of O2 and the volume. So when I open this valve, that's going to change the volume, because now both gases are going to be able to spread evenly throughout both sides of the flask. Now, the easiest way to do this, I think, is to just imagine that we're going to allow the gases to just spread out before anything reacts. Now, of course, as soon as the gases come together, they're going to start reacting. But let's just, for the sake of moment, just imagine that both gases fill up both sides of the container all together once I open the valve. So that way, we can treat this as a Boyle's law problem. P1 V1 equals P2 V2. And then we can figure out what the new pressures are going to be before we even look at the reaction itself. Okay, so let's do that. So we'll do NO first. So for NO, right, so we'll do NO first. So that's going to be P1 V1 equals P2 V2. So the initial pressure and volume is 0.50 atmospheres. So that's going to be our P1. Oops. 0.55, 500 atmospheres. And our initial volume is going to be 4 liters. And then that's going to be equal to P2 V2, what our final pressure and volume is. So we don't know what the final pressure is going to be. We're going to calculate that. But we do have the final volume, because when we open this valve, then the gas will fill up the whole 2 sides. So it's going to be 4 liters plus 2 liters gives us 6 liters. So P2 we don't know. That's what we're going to solve for. And then the new volume, once the valve is open, is 6 liters. So now all we need to do is solve for P2. So divide both sides by 6.00 liters. 6.00 liters. Liters cancels out. We got atmospheres. So then the pressure, the new pressure of NO is going to be 1/3 atmospheres. So this is going to be 1/3 of an atmosphere. Okay, so this is for NO. Now, what about for O2? We'll do the same thing. So for O2, the initial pressure is 1 atmosphere. So 1.00 atmospheres. And the initial volume is 2 liters. And that's going to be equal to our final pressure and final volume. Again, we're gonna solve for the final pressure, but our final volume again is going to be 2 plus 4 is 6. So we're going to have P2 multiplied by 6.00 liters. Again, divide both sides by 6.00 liters. Liters are going to cancel out. And then when we calculate this out, again, the partial pressure P2 is going to be equal to 1/3 atmospheres. So now we know what the pressure is for each of these before it reacts. So we're assuming nothing's reacted at this point. We're just equalizing or finding out what the new pressures are going to be under the new volume. Okay, now we can start to think about what the reaction is going to be at this point. But before we get to that point, there's one thing I want to point out. Now, notice how we are told that the temperature is constant. Now that the reaction is going to take place, look, both gases are under the same volume. Before they were not under the same volume, but now after we hypothetically or theoretically allowed the gases to spread out evenly throughout the whole vessel, now the reaction can take place, and now the volume will be constant during the reaction. So we have constant volume and we have constant temperature. Now, under those conditions, if you notice here, if we take the combined gas law equation, P1 V1 over T1 N1 is equal to P2 V2 over T2 N2. The thing that we want to keep in mind is this combined gas law equation is really the only equation that we need to know, is because all of the gas law problems or gas law equations are part of this one. So now we can see what equation are we left with if we eliminate whatever is constant. So because whatever is constant is not going to be in the equation, we don't need it in the equation because it's constant. It's going to cancel out anyway if we put it in the equation. So volume, in this case, is going to be constant. Now that it's 6 liters, so we'll get rid of the volume, and then the temperature is constant, so we can get rid of temperature. And then what we're left with is P1 over N1 is equal to P2 over N2. And what does that tell us? Basically, this tells us that pressure and the amount of gas is going to be proportional. That means that whatever I do, this ratio is going to stay the same. That's what the equality means. So if I start with one set of conditions one pressure and one set of amount of gas, that's going to have a certain ratio. If I change my N1 to something different that's going to be N2, well, if these two sides are equal, then my pressure is going to have to change in order to keep the ratio the same. So this ratio is equal to that ratio if I change something. So, for example, if I double the pressure, what must happen to the amount of gas to keep the ratio the same? Well, that's got to double as well. So they're directly related to each other. So if I double the pressure, I've got to double the amount of gas so that the ratio is the same. And guess what? The 2 and the 2 will cancel out and we get back the ratio, right? So this is important. Why? Because this is telling me that pressure under these conditions, pressure is proportional to the amount of gas. So why is that important? Well, that makes the problem easier because now, just like I have a balanced equation here, I can use the mole ratio to help me convert from one thing to another. I can use pressure now as if it was moles, because now the mole ratios here are the same as pressure ratios. So now I can go ahead and use my balanced equation. Okay, so now that I have this, I'm going to use my balanced equation. And so let's go ahead and rewrite my balanced equation here. So I have 2NO gas plus O2 gas gives me 2NO2 gas. Okay, so I'm going to do my ICF table. So my initial amounts of everything, the change that occurs during the reaction, and the final amounts that I end up with. So here I have 1/3 atmospheres. Here I have 1/3 atmospheres. And of course, at the beginning, I have 0 atmospheres of 2NO2. Okay, now notice that they're giving me amounts of each of the reactants. I don't know which one is the limiting reagent, so I have to figure out which one of these is going to end up disappearing first. The one that runs out first is the limiting reagent, and so that's going to stop the reaction. So the amount of product is going to depend on the one that runs out first. Okay, so how do I figure out which one is the limiting reagent? Well, I can use the mole ratio, 2:1. So let me take the amount of oxygen, and so I can calculate from the amount of oxygen how much NO does this amount of oxygen need in order to react completely with that oxygen. So I can use ratio. So I have 1/3 atmospheres of oxygen. I'm going to convert that to atmospheres of NO that's needed to convert, to react completely with 1/3 atmospheres. So since it's a 1:2 ratio, that means that for 1 atmosphere of oxygen, I need 2 atmospheres of NO. And so when I calculate this, I get 2/3 NO. So 2/3 atmospheres, that should be 2/3 atmospheres of NO. So this is the amount of NO that I need to react completely with 1/3 atmospheres of O2. But you'll notice I only have 1/3 of atmospheres of NO. I don't have enough of the NO to react completely with all of this O2. So that tells me that I don't have enough of this, so this is going to run out before this does. So this NO is my limiting reagent. So NO is the limiting reagent. So now I know that this is going to react completely. This is going to be gone. This is going to run out first. So at the end of the reaction, my final amount of my NO is going to be 0. So I'm not going to have any NO left over, so I'm going to have no pressure. So 0 atmospheres for the NO. So there's a change here of a minus 1/3 atmospheres. So I lost 1/3 atmospheres of my NO, and because this is a 2-to-1 ratio, then if I lose 1/3 atmospheres here, then that means I'm going to lose 1/2 that amount. What's 1/2 of 1/3? That's going to be 1/6. So I lose 1/6 atmospheres of my O2. And if I subtract 1/6 from 1/3, right? So what's the same as 1/6? So minus 1/3. So that's going to be, this is the same as 2/6, right? So if I take 1/3, 1/3 is the same as 2/6, right? And I subtract out 1/6, then that's going to give me 1/6 left over. So that means that my final amount after the reaction is completed is going to be 1/6 an atmosphere of O2. So I have 0 left over of NO. I have 1/6 of an atmosphere left over for O2. And then also keep in mind that I have 2 here. So here, if I lose 1/3 of the NO, it's a 2-to-2 ratio or a 1-to-1 ratio. So it's going to be the same here. If I lose 1/3 here, then that means I'm going to gain 1/3 of an atmosphere of my product, which is going to be meaning that I'm going to have 1/3 of an atmosphere of 2NO2. So what are they asking us? They say determine what the gases remain at the end of the calculation. We did that. So what gases remain? It's going to be the O2 and it's going to be NO2. And calculate their partial pressures. We did that. So 1/6 of an atmosphere of O2 is left, and 1/3 of an atmosphere is left, is created of NO2. And so that's how you solve this problem. Let me just check. Okay. And so that's it. So that's how you do this problem. I hope this was helpful. If you enjoyed this video, if you learned a lot from this video or anything from this video, then please, by all means, like the video, share the video, hit that notification bell, hit that like button somewhere over here, somewhere. Find it, click it. Also, subscribe to my channel. Do me a favor. Also, make sure you click that notification bell, hit that, click the all button so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help with, or a topic you need covered, then let me know. I would love to do that for you. Thanks for joining me, and have a great day.